Earlier we learned how to draw graphs using parametric equations and a single dimension. Today we're going to extend that to multiple dimensions. To do so, we'll look at this problem. A 29-year-old lemming runs off of a 25-meter high cliff at 8 meters per second. He was running into a headwind which decelerates him at 1.2 meters per second squared. I'd like to make a graph of the position of the lemming throughout his flight, and we can use that graph then to predict when he will land and how far away from the cliff he'll land, and we can even use it to figure out how fast he was going when he pummels into the ocean depths below. Before we get started, let's make a list of the known quantities and any assumptions we might need to make. Remember that this is a multiple dimension problem, and so there are both horizontal and vertical quantities. Horizontally, we can say that the initial position is 0 and the final position is unknown. That's when he hits the water. We were told that the initial velocity is 8 meters per second. The final velocity is unknown. It's not going to be 8. It'll be a little bit slower because he was running into a headwind, and that headwind will have slowed him down. But that does mean that we know an acceleration. We were told that he's decelerating. Let's assume this to be purely horizontal deceleration, and we'll call it negative because it's slowing him down instead of speeding him up, 1.2 meters per second. Vertically, we were told the initial height of 25 meters. The final position will be 0 when he hits the water, but when we're making a graph, we really only need the initial settings, the initial position, the initial speed, and the acceleration, because the graph will look at many different points in time, and so I'm not going to put 0 meters down. Even though we know the final position of the lemming vertically is going to be 0 because he's going to eventually hit the water, when we make a graph, we don't put in any final positions. We're going to let the calculator calculate lots of different positions. All we need to do is to figure out the initial settings. So 25 meters is his initial height. The initial speed vertically was not told to us. We're going to assume that he's running off the cliff horizontally and that he didn't jump up at the end, and we'll call that 0 meters per second. We also weren't told where this lemming is, but let's assume that he's just in a general place on Earth and is falling with the typical gravity of negative 9.8 meters per second squared. Now let's look at making a graph of the lemming's flight. Last time we made a position versus time graph. Today we're going to make a slightly different type of graph, which is a pure position graph. It'll have vertical position along the y-axis and horizontal position along the x-axis. Let's label that a second. X position and y position. And so in order to make a graph, we're going to need an x position formula for our x equals equation, and we're going to need a y position formula for our y equals equation. Remember, the position formula is simply the initial position plus the initial speed times time plus half of the acceleration times time squared. Both our x equals and y equals equations are going to look quite similar. They'll have the same basic position formula shape, but they'll have different numbers. For the x equals, our initial position was 0, our initial speed was 8, and our acceleration was negative 1.2. So we will say 0 meters plus 8 meters per second times time. Remember, we're going to need a variable, plus 1/2 times negative 1.2 times t squared. Vertically, if we look back, the initial position vertically was 25. The initial speed was 0, and the acceleration was the familiar negative 9.8. So our y equals equation will be 25 meters high plus 0 for an initial speed times time plus 1/2 times negative 9.8 times t squared. So to create the graph, I must first make sure that I'm in parametric mode. I am from last time. Now I'll go to y equals, clear out any equations I have there, and type in the ones that we've just written. 0 plus 8, and the variable button creates a t, plus 1/2 of negative 1.2 t squared. For our y equals equation, we've got 25 plus 0t plus 1/2 times negative 9.8 t squared. Some of you might be thinking it was kind of silly for me to put in the 0 and the 0t. Honestly, they don't need to be there. If you wanted to, you could type it in without those. I only put them in there to kind of show the symmetry between the x position formula and the y position formula, and to show you as a teaching tool that I didn't just forget something or ignore it. It just happened to be 0 in this specific example. Now we've got to think about the window settings. Remember, when we're thinking about window settings, one of the first things we should consider is how much time we think the flight will take. I don't honestly have any clue as to how long it's going to take to fall. 25 meters high, that's about the height of the gym probably. So 3 seconds should be sufficient. Let's keep it there for now. The X position, I think it would make sense maybe to go out by 5. I'm honestly guessing. I don't know right away. So let's go out by 5, and the graph I have below me has 6 spaces across. So let's go from 0 to 30 by 5. We'll see if that's enough. I do know the extremes of the y-axis. The highest the y-axis needs to be is 25 meters, because that's the height of the cliff. The minimum, it would make sense to be at 0, and that would mean we would use a scale of 5 meters high to fit on the graph that I've got shown on the PowerPoint behind us. Let's graph it and see if we need to make any adjustments. That looks like a pretty good graph. I can see all the relevant details, and it looks like he splashes into the water about maybe 15 meters away, but I'm getting ahead of myself a little bit. Let's write these answers down a second. The time settings we used were 0 to 3 seconds by 1/10 of a second. The x-axis values we used were to go up by 5, which puts us from 0 to 30 on the graph that we've got here. 0, 5, 10, 15, 20, 25, and 30. We should always label our axes. These are in meters. And then the y-axis, we went by the same scale of 5s. But the graph I had only has 5 rows, so that only goes up 25 meters high. Let's see if I can write a sideways M. It's about as neat as the rest of my handwriting, huh? And the graph, if we illustrated, it went and it fell pretty much down here at 15. I would expect you to have slightly more accuracy than me when drawing a graph. I'm trying to do this on a computer. A little difficult. So let's look at answering the 3 questions that were asked now that we've got a graph. One question is, when does it hit the ground? We can use the trace tool to figure this out. If we hit trace, we can walk along this graph. As I'm just walking along the curve, it looks like between 2.2 and 2.3 seconds is when my height, my y value, goes from positive to negative. So let's try just typing in 2.25, and there we get a height that's just barely positive. We could go a little bit longer in time, 2.26. Now we're just 2 centimeters below the surface of the water. You could play this kind of guessing game back and forth and eventually calculate with several decimal points worth of accuracy when we hit the water. For now, I'm going to leave this at 2.26 seconds. That's pretty good. That's just 2 centimeters below the surface of the water, and it looks like we went 15 meters and 1 centimeter when we hit the water. So we estimated that the time when it hits the ground is 2.26 seconds. At the same time, we found out the horizontal position of the lemming at this particular moment in time was about 15 meters. So we would say the final position horizontally, SFX, is equal to about 15 meters. We can also use the calculator's tools to help calculate the velocity at that particular moment in time. To answer this question, we can use the calculate tool, which is second trace, and the values down here, 3 and 4, will help us calculate velocity. What dy dt is the change in y position over the change in time. Change in position over change in time, that's velocity. So dy dt would give us the vertical velocity, and dx dt would give us the horizontal velocity. Let's do dy dt first. When you hit enter, then you need to type in the specific time, which you want to know how fast you were going at. We said 2.26 was about when you hit the water. So the velocity at 2.26 is negative 22 meters per second. Let me write that down a second. Using a time of 2.26 seconds, we found the vertical velocity to be negative 22 meters per second. If we repeat these steps, second calc, but repeat them with the horizontal dx dt, and type in 2.26 seconds and hit enter, this calculates how fast horizontally we were going. Remember, we started at 8, but we were going into a headwind, so we've slowed down to about 5.3 meters per second. Let's just round that to 5. Vx was about 5 meters per second. The combined velocity is the sum of these two numbers. However, we need to find the sum of these two numbers as vectors. We can't simply add them together because they're in different directions, but we can draw a picture and use some trig to find it. Vertically, they're going down 22 meters per second, and horizontally, they're going across 5 meters per second. The combined velocity would be this resultant vector, and that is the hypotenuse of a right triangle. And so we can find the hypotenuse of this by using the square root of the two legs squared, 22 squared plus 5 squared. And a quick calculation gives us a combined velocity of about 22.6 meters per second. Let's round that to 23 meters per second. It might also be useful to calculate the angle at which we entered the water. So the angle at that particular moment we could measure from horizontal or from vertical. If we find this angle, we would use inverse tangent of the opposite. That would be 5 over 22. At first glance, that looks to be about 20 or 30 degrees maybe. If we do the inverse tangent of 5 over 22, we find about 12 degrees. It's reasonable. And it's good to tell that that is measured from vertical.